This is the 15th episode of Advanced J1939. In the next couple of episodes, I'm going to discuss termination. So if you're familiar with the J1939 standard, we know, or CAN standard, we know that we have terminating resistors on either end of the network, so 120 ohm terminating resistors for J1939. If I were to do a simple model of this, I can take the two terminating resistors, put them in parallel, and we end up with 60 ohms for them. So that's what I have here. We also have capacitance between the wires. So we have basically the definition of a capacitor. We have a conductor, which is the copper cable, and we have a dielectric or an insulator, which is the colored insulation that's on the wire. And then we hold the wiring a certain distance from each other because they're twisted. We hold them tight. So we have this distance between, if you would, these two plates of a capacitor. So we can model those for this approximately 7 meter, about 20 feet of J1939-15 cable that I have here. We also have a series resistance, which is just the copper resistance of the wire, and we have also some inductance. So even though it's not coiled, if you would, it is a piece of straight wire has inductance, as I've talked about in other episodes. So if I look at getting this information from something such as this press-to-light wire for 1939-15 spec cable, we can see that they specify a, a capacitance of about 12.5 picofarad per foot nominal. So a farad is a unit of measure of capacitance. Pico is 10 to the negative 12th power, so a whole bunch of zeros in front of it. It doesn't seem like there's much capacitance, but nonetheless, once we start getting up into speeds of the 500K, 250K, then this capacitance becomes an issue. We also have if you would, the resistance of the wire. We can find wire resistance calculators for that. We can take 18 gauge wire and go calculate and find what that is. But it's approximately this about 125 milliohm for each of the 20 feet or 7 meters approximately of the data link cable. So we'll go ahead and I'm going to first, before we get into terminators and why we need them for, I just want to make sure that we understand that there's capacitance here. And the capacitance is something that we have to deal with. And if I take a look at a simple circuit such as this, what I have here is I have no capacitance in this model. If I were to run, basically, if I look at the switch at 1 second, it opens. So right now it's closed, and at 1 second it opens. And if I look to see what the voltage is across that, it's pretty simple. If we take a look, we have we're sitting at the 1 volt. The switch opens. When the switch opens, this is a vertical line. There is nothing here. This is a complete step function. It drops down to 0 volts instantly. So there's no delay. There's no ramping of this. It just drops instantly. If I were to, we'll go ahead and put a capacitor in the circuit. So I'm going to put something in here, and let's give it a value of, I don't know, let's start off with a value of perhaps 100 microfarad. So we're going to start off with 100 microfarad, and 100 microfarad, a micro is 10 to the negative 6 power. So I now have a capacitor in this circuit. So what's going to happen is as soon as the switch opens, we're going to have something happen. So let's go ahead and take a look and see what that looks like in the time domain. And we can see that what happened here is my vertical line is gone now. It is ramped, and it's ramped down, and it takes, if I look at this as at 1 second, it took about 50 milliseconds for this to basically reach close to 0 volts. So as this capacitance increases, so let's go from 100 micro to, let's go make it 10 times, so 100 mil. And let's see what happens with that. We run it. So the more capacitance that there is in this circuit, the longer this decay it takes. So the longer it takes for this to drop down. So now, even though the switch closed at 1 second, or switch opened at 1 second, we can see that it took quite a while before it got over here to where we could call it close to 0 volts. In theory, it never goes to 0 volts. It's an exponential decay. In practice, we say we call it a time constant. It's something you can study on your own, but after 5 time constants, we say that it's effectively 0. So this is some of this engineering. It's close enough kind of philosophy. So somewhere down here, we're going to reach that 5 time constants or 5 tau. We're going to reach it, and we're going to say, yeah, it's close enough to 0. It's not exact, but electronics isn't an exact science. It can't be, because there's variation in parts, and there's things such as this capacitance that we have to worry about. So in practice, we really never can eliminate all the capacitance. So we can we just have to deal with the capacitance. So a couple of ways that I can deal with it. Let's say that we have this. I can either, if the capacitance is fixed, if I can't change it, what I can do if I want this to drop quicker is I can reduce this resistance. So we're going to change it from 120 ohms down to 12 ohms. And let's take a look and see what happens in our time. We can see now that because of that, it's changed this dramatically. So my time for this to to go near to 0, or this 5 tau that I talked about, it's now something like 80 milliseconds or so. So we went from we dropped that considerably by reducing this resistance. Conversely, if I were to take this and let's go the other way, let's make it 10 times greater than what it had been originally, and you can imagine what happens is this really starts to ramp, and I can't even show in this because we're nowhere near 0. We're sitting at about half a volt here, or about 4/10 of a volt. So um, this is the basics, I guess, of why I have to have this capacitor here, for why I have to have the terminating resistor. I need to be able to rapidly pull down the signal. So when back to our transceiver, when these change states. So if I were to run this simulation, we'll go ahead and run it real quick. I run this simulation, and what we're going to see on it, let's go ahead and get rid of this. I can see that I come up and I have some of this noise, and this is the capacitance and the inductance. Together, we end up with some what we call oscillation, or you might look like an AC signal. We have it. I'm now up. I've got the can high and can low are in a dominant bit state, and then when the switch switches off, then we drop back down to our 2.5 volts approximately, and in so doing, I have this ramp. And so this ramp is the same thing that I showed you in the other simulation. This ramp that you see here is the capacitance that's in the network. And so let's take a look, as I showed you before with the terminators. Right now I have this modeled with the 2 terminators. So let's go ahead and let's take one of the terminating resistors off, and we're going to set this to 120. This capacitance, as I indicated, is from the wire itself. So the insulation, the 2 pieces of wire and the spacing between them. By definition, that's a capacitor. So let's run this now with one terminating resistor, only one, so we're missing one. So let's take a look at our time domain now, and you can see that just like I showed in the other simulation, as I change that resistance, I'm changing this ramp and the rate of this ramp. So this ramp is now, it takes longer for this to get back to this state. So this is the dominant state. This is the recessive state. I need to get there. I can't let this go for too long. I have to get to this point pretty quick. We'll go ahead and I'll make another example here. Let's go ahead and as I showed before, let's take our terminators and let's do something, let's make this 1,000 ohms. And let's say that this actually happened to one company that I worked for. The terminators were accidentally, they pulled, instead of when they made them, they used 1,000 ohm resistors instead of 120. And it only really got noticed when we ended up with 2,000 ohm resistors on the same machine, and in so doing, we ended up with communication issues, as you can imagine. Believe it or not, there's probably a bunch of those vehicles still running around that have 1,000 ohm resistor and 120 ohm resistor, but it's there's enough termination there that it didn't cause a problem, even though it isn't a specification. So here's something with 1,000 ohms of termination. As you can imagine, how long does it take me? So we're looking at 1 bit of in this for a 250K CAN bus, which is 2 2 microseconds in duration. So 2 microseconds in duration. I have this one bit. Excuse me, this is 500K. It would be 2 microseconds, 4 microseconds for 250. Yeah, okay. So looking at this, this is one bit at 500K. We can see that we have from this period of time, 2 microseconds, the transceiver switched to a dominant state, and then for 2 microseconds up to this 4 microsecond time, we then try to go to a recessive bit. And if it takes me too long, this is going to look like it's a dominant bit. And then it's going to look like it's not. And so what this is going to cause is errors. So we only have a period of time that these have to get down to where it's the logic level, the voltage level is one where it's going to be called a recessive bit. Now, to guarantee that, I don't know. I probably have to have going from dominant to recessive. I probably have to have a good, 800 millivolts for the one direction, or close to a volt for the dominant direction. For the recessive, going back to recessive, it's probably about 500 millivolts, I believe, that I have to be below. We could look up the specification, but you can just imagine you have to get back below some value, and we'll say 500 millivolts. It's taken me a long time to get back below that. We'll go ahead and put this one back on. As you can see, our difference in voltage here, my difference in voltage on the gray, we can see that we're not getting down to this half a volt or so until we get to this point. So there's a lot of time that has accrued. It might not seem like a lot of time to you. It's 0.4 microseconds, so 4/10 of a microsecond. But for a CAN transceiver, this is long enough that this is a problem. So in order for CAN to work, I have to put this termination in place. So we'll go ahead and put this back to where it's supposed to be. We'll show this one more time. And you can see that we're reaching our half a volt or so here really quick. So it's only whatever it is, 0.025 microseconds, for example. So it's a very, very short period of time. So this allows the CAN transceiver to determine that this is a dominant bit and that this is a recessive bit. So as indicated, if we were to pull up the data spec, and so looking at the data sheet, for example, for this CAN transceiver, there's these timing characteristics. Yes, way beyond the scope of these videos, but if we look here, we can see that there are specifications for how much time that this has to be for the states to be determined. So if I look at this schematic over here, we can see one thing called hysteresis, something else we probably won't discuss in this course. But looking at this, here's our ideal signal, right? And so here's the real signal. We can see these ramps. We can see the time for it to go up, the time for it to go down, and where we consider this to be dominant and where we consider it to be recessive. So as indicated, about 500 millivolts and about 900 millivolts or so. So in order to get to those states, to get to those voltages, which also have a tolerance on them, so I can have some variation from CAN transceiver to CAN transceiver. They're not exact. There's a little difference in them. So in order to get to this point, I have to be able to, this voltage point, I have to rapidly be able to do that. And so that's these times that we're referencing here, this delay times for these things to be. So there's requirements on that. And so our termination is what permits us to, okay, let's take a look at what happens if I have no, we can see here that I've removed the termination. Let's take a look at what happens now when I run the simulation. As we can expect, we get our the transceiver switches to a dominant bit here at 2 microseconds. We stay at the dominant bit state for 2 microseconds, and then so that means at 4 microseconds, the switches are going to open. And what we're going to see is that the time for this to decay is really, really long. So this looks like a dominant bit the entire time. So this is supposed to be a logic 0, supposed to switch back to a logic 1 at this point, and instead it's staying at this dominant state, the voltage for a dominant state, which makes it look like the bus is continually occupied. What this is going to do in real practice, if I took the termination off of the network, and it depends on how long the network is, as I can show, and how many transceivers are on the network. What happens is this time will become so long that it looks like the bus, as soon as one controller comes on to put a dominant bit on the bus, it makes it look like the bus is in use continually because it's going to maintain at this dominant state. Eventually, this is going to drop down, and then we'll get another bit. And we'll take a look at that on a real oscilloscope in the next lesson. So I'm going to go ahead and I'm going to shorten the network up. So if I took it from the 20 feet, let's take it down so that it's only 2 feet. So let's make this be 250 or 25 pico. So we're going to reduce that to 25 picofarad, which is also then going to reduce these down to 12.5. We'll do that. All right, I'll be exact. And 0.5. And we'll go ahead and leave the inductance the same since it really isn't a factor here. So let's see what happens now that I've reduced the capacitance, even though I have no termination. So let's take a look at this. And as you can see here, it reduced this to a point where it still isn't going to work. But at some point here, when I get a really, really short network and I have more transceivers on this, you may actually be able to communicate on a very short CAN network, even though you have no termination. The controller, the resistance within each of the controllers themselves, may be enough to pull this back down, which is why maybe if you had like a bench harness made up, and I've seen this many times where there's no termination on it, it's a very short piece of CAN cable, it works fine for reprogramming, or it works fine, for bench programming, or for just a simple display or test setup. But once I start increasing this capacitance, once I start increasing the length of the network, then this becomes a factor. The other thing that changes this is if I don't use the spec cable. So if I decide instead of using, I'm going to get cheap, and instead of using this cable which has this capacitance, and instead if I use something which it has a much higher capacitance, I can increase this to a point, though, even though I have termination, I can start impacting my network. This is one of the reasons it's important to use the specified cable. I know some manufacturers don't. But if your network is short enough, they probably get away with it, even though it's bad practice. So I do see those kinds of things out there. It may not cause a problem all the time, but it may be at the point where it just puts the system right at the point where occasionally I might have some CAN errors because of this misinterpretation of bit states. One other thing that people talk about with termination, and I'll go ahead and add the termination. With this network, the way that I have it drawn here now, we'll go ahead and throw this back up to our 250 picofarad. The way that I have it drawn right now, it has, I guess I could call this reflection. So there will be, without the terminating resistor there, this doesn't really model this within this circuit lab. It's not going to model this effect. But what's going to happen is that the signal energy will travel through the wire. It will go out to the end of the wire, and it will hit the end of the wire, and it will effectively bounce back. So you can think like a clothesline. So this is similar to like a clothesline, and if I flip the cable, what's going to happen is I'll have a wave that will go down the cable and hit the other end. It's stationary or attached on this end, and so then what happens is that waveform propagates back through the other direction. So you can imagine if I hit the end of this and I have noise that's coming back down the other end, it will impact my signal. So one of the things that the terminating resistor does, if I put a resistor here, it hits the end of this. When it hits the end of this, it's like having a damper, I'll call it, or something like a shock absorber, if you would, at the end of the clothesline. And so what that does is it absorbs that. What this means in reality, though, the energy progresses down or propagates down the line, and when it hits this end, it just dissipates as heat through the resistor. So that energy, instead of flipping back and hitting the end, bounces back through. In reality, for 500K CAN, even 500K CAN, this thing of reflections, you can see the noise. If you look at it with a fast enough scope, I can see the noise, but it really isn't that big of a factor. It's probably a little overstated, I guess, in some of the theory information that's out there. The purpose for the terminating resistors are to absorb the energy when it hits the end. Yeah, it does, but that's not the biggest reason for the termination. The biggest reason for the termination is, as I've discussed here, to pull this back down once we go from dominant to recessive. I need to rapidly allow this to decrease. And to do that, I have to have termination. You might ask, okay, if this is good, then why not make it something like 10 ohms instead of 120 ohms? Because what that's going to give you is, if we take a look at this, that gives me a nice, very clean waveform, right? Look at how quick this decays now. This decays rapidly. The problem with making as I go with too much termination, and you might see this if you've seen a network with 3 terminating resistors on it, what happens is I'm now requiring more current. The lower that this goes, if I were to put an ammeter here, as you can imagine, this is now going to drive more current, and it's more current than the CAN transceiver can drive. So the CAN transceiver is designed to drive basically 60 ohms of resistance into 60 ohms of resistance. The lower I make this, the lower the CAN voltage is going to be, because the lower I make this resistance value, because what happens is this just cannot source that much current. At some point, this is going to look, if I were to put something like this, if I were to make this 0 ohms, I'm not sure if the simulation will run with this, it'll probably get angry. Maybe. There we go. If I made that 0 ohms, as you can see, what happens is this just stays at 2.5 volts. We never even get a dominant bit, right? We can't see anything as a dominant bit. So this is a short across the data link. So we can go between the two extremes. This is what a short looks like. If I were to take this out and remove this, let's do this. Okay. So we go between the two extremes, between a short and an open. And if I look at this as the open, as we saw previously, then I can't get back down to the recessive state. So hopefully this helps you get a better understanding as to why we have termination. In the next episode, I'll break out the oscilloscope. We'll put this on a real network, and we'll prove that, that we can see some of this with an oscilloscope on a real network.